Good morning, everyone. How's everybody doing? Happy Wednesday. Hope everybody's doing well. So, of course, let me know if you have any questions in the chat. Happy to answer questions. Otherwise, we'll continue on with bond energies. And so, quick recap, we were talking about the different types of energies. So, we mentioned potential energy. And so, that's what we're going to be talking about, right? So, the potential energy stored in bonds, and that's compared to kinetic energy. So, remember, kinetic energy is the energy of motion. And so, now we're looking specifically at potential energy. So, the potential energy involved in bonds, so making and breaking bonds. And so, if we look, chemical reactions involve breaking bonds in reactant molecules and making new bonds. And so, we can figure out how much energy, or what's called the change in enthalpy, delta H, of our reaction, can be calculated from the cost of breaking our old bonds to our income, as we'll call it, since making a bond is thermodynamically favorable, so you get energy back from that process. And all these calculations assume that we're in the gas state, and so that's where we say we can estimate it when we look at reactions in real life. Maybe it could be in other states, and you can't account for that, but we won't get all into it right now. So we're just talking about how to calculate in the gas state. And this also assumes homolytic cleavage. And all that means is if we take a bond, let's just take a simple single bond. And then if it undergoes homolytic cleavage, that means each hydrogen gets one electron. So, right, it says each atom gets half your bonding electrons. So here we have two bonding electrons in our single bond. And so we'd be calculating the energy to do this process. And just to compare, let's at least define what the other type of cleavage would be. And so that would be heterolytic. And this is kind of an aside, but still good to know. You see it. So heterolytic would mean that they break unevenly. And let's look at one example of that. So one example are these nitrogen boron compounds. And what's pretty cool is you can figure this out from your Lewis dot structures. So this is where your Lewis dot structures show their power. And so we can draw ammonia like this, right? So this is our ammonia. And notice that it has these two electrons. And then if we draw BF3, if you remember, boron only has three valence electrons. So a little odd. And it's a little odd in that boron can make these structures that violate the octet rule. But because of this, this kind of makes them susceptible to making these compounds and being attacked from nitrogen. So then they make a bond like that. And I drew their bond with an arrow to show that it's heterolytic. All right. So that's the comparison. But again, in all these scenarios, we're assuming homolytic cleavage where it's evenly split. And so with that, we'll look up our bond energies. So basically we have a table of average bond energies. Again, this is just to give us an idea. So the actual bond energy depends on other factors. Again, what state it's in and, the real world, what reaction conditions it's under. But we can still use our average bond energies to again estimate our change in enthalpy. And again, we're assuming we're in the gas state. So this is important here. I would kind of star this. So bond breaking is endothermic, which means you have to put energy in. And let's put energy in. And you can think of like heating something up, right? That's a form of putting energy into a system. And we also symbolize this with a positive enthalpy value. Again, that means we're putting energy in to break our bond. And then bond making is exothermic. So like I mentioned, that's a favorable process. And so you get energy back from that. And so that's symbolized by a negative value. And so I'll put energy out. And an exothermic process would feel hot. So maybe energy would be released in the form of heat, could be light, but mainly heat, especially with exothermic. So exothermic means heat. So it means this negative value, but you also will feel the heat from the reaction. And that's the heat of that change in enthalpy. And so that means that bond breaking, so like I said, you have to put energy in, but this means that it might feel cold to us. And we can think about like an ice pack. You know, those ice packs, you crack them. And I remember correctly, those ice packs are usually ammonium chloride. And then you break the little seal and it starts solubilizing it, which is an endothermic process that requires heat. And again, since your body would then be supplying the heat, then it would feel cold and cool you down. And so similarly, right, an exothermic process would be some sort of exothermic reaction. So sometimes you can have like some iron powder and those like hot hands. And of course, you expose them to air and that sets off an exothermic reaction. And our formula for this can be summed up here. And so this means we're going to take the sum of all the bonds that we break, and then we'll add that to all our bonds formed. And remember, bonds broken is positive, bonds formed is negative. Then we'll add those two together and then compare. So before we do the math, we'll just at least go through the general trends. So like we've kind of seen, we've seen a single, double, triple bond. And with the increase in electron sharing, obviously that's going to increase the energy. Sorry for bumping. And we see that in our carbon. So it goes from 347 kilojoules for a carbon-carbon bond up to 837 for a carbon triple bond. Same thing with nitrogen. Again, that triple bond is a lot stronger. Bond length also plays a factor. So even in our single bonds, and so this is more of a radius effect. So if we compare bromine, fluorine, so fluorine has a smaller radius compared to bromine, bromine. And so that means this bond is slightly weaker. And so that means bonds tend to get weaker down the column. So right as you add more shells, that's more diffuse, so weaker bonds. And then they tend to get stronger across the periodic table, especially as you head towards the more electronegative elements that are going to be holding those electrons tighter and making a strong bond. And so to do these problems, you would need to reference a chart, or on an exam, I would usually provide like the values you would need. So we'd look at a reaction and I'd, list the relevant on energies. And so we can just appreciate this chart for now. anytime you look at one of these bond energy charts, you want to note what your bond energy is given in. So all this time we've been working in kilojoules per mole, but you could see other units. All right, so let's go through this first example here. So how do we do this? We have to look at the reaction, sorry. Now we can actually see our reaction, and I'll rewrite it so it's clear. And so we have our starting products, our starting reactants over here. So methane, that's CH4 plus chlorine, and then gives us this chloroform. So we replaced a hydrogen with a chlorine. So just kind of note what changed. So maybe you can start, highlighting, okay, we need to break this bond. We made this bond. And we also probably broke a chlorine-chlorine, and we made an HCl bond. And I think initially it's a good idea to write it out kind of explicitly like I did. You don't have to focus so much on the geometry right now, but we just want to write out, what's being broken, what's being changed. And in this case, we were just in a 1-to-1 mole ratio. But if you're working with several equivalents, go ahead and write out, your 4 hydrogens, just so you can really see it all. That will help you understand, especially initially. All right, so now that's what this energy chart walks us through. And so we said the process was, again, endothermic. We have to put energy in. And so here is our change in enthalpy, positive, for breaking that CH and chlorine-chlorine bond, like we had identified. And they've kind of done the math, but we haven't done it. And so they already told us that this process is exothermic, but we need to prove that with numbers. So let's do that. And this is how I recommend laying out your work, is you want to have a separate section of bonds broken, and then we'll tally those up and then look at our bonds formed. And maybe put next to them, the symbols that they're going to be at the end. So you don't have to worry about the signs until the end when we're trying to add them together, if that makes sense. And so we said we need to break our CH bond and chlorine-chlorine. And so I like to write that out. And we can put 1 here if we need to, because you might have several. And so let's grab the value from our chart. We'll scroll back up and kind of help us. And so we have CH here. So 414 kilojoules per mole, and we just have 1. We don't need to multiply it by anything. So that's 414 kilojoules for that process. Now let's see how much energy it takes to break our chlorine-chlorine bond. So find that on the chart. That's 243 kilojoules per mole. Again, we only had 1. Oh, 243, right? I forgot the number as soon as I scrolled back. And so let's go ahead and add those. Four 14 plus 243. I get 657 kilojoules. And again, that's energy in that we had to put in. And so let's see how much energy we get back. So now we're kind of here at this transition state, or however they're trying to show this. And now we say, well, now we need to make our carbon chlorine bond. So this was one new bond that we had already identified. And then, of course, also make our HCl bond. And so let's tally that up and look at those numbers once again. So carbon, chlorine, and HCl. And I'll just denote there's one. Okay, carbon, chlorine, 339 kilojoules per mole. So that's 339 kilojoules for one bond. Let me look up HCl. 431 kilojoules per mole. Again, we have one. So now I'm going to add them up. Let's go ahead. I'll just use a calculator. Oops, wrong one. So 770 kilojoules. But then that was negative, remember? Because that we got energy back out from that bond formation. We can put a negative sign, or right, that was exothermic. And so now we have to add them together to see whether the overall process was endothermic, so whether it was positive and required more energy, or whether the overall process released energy. And you can probably already tell our number is going to be negative, so this is an exothermic process, but let's see how negative. And so now this is telling us that 113 kilojoules of energy was released in this process. And so this would be an overall exothermic. Again, heat released, energy would feel hot to you. Questions about that one? I'm just going to pause there for a second. All right, let's try this next example problem. I'm going to leave this up, give people a little bit of time. As always, you can pause it if you're watching later. So my recommendation, especially if you're stuck, is again, start off by drawing everything out. So now I'm not focusing on the geometry, but just drawing out, what's connected. Sorry, I swear the spring allergies have started. And so I also had mentioned, right, draw out however many equivalents you're making or adding. So we have two equivalents of water here. So let's draw out two water molecules again so we can really see. We make 4H2. So I'm going to draw all those out explicitly. And my CO2. All right, so now I've drawn everything. And so now if we start looking at, oh my, right, we're breaking a lot of bonds. So we have 1, 2, 3, 4 CH bonds to break. And then looks like we have to break all these OH bonds. So that's 1, 2, 3, 4 OH bonds. And we'll make 4 HH bonds. And then, of course, form 2 carbon oxygen double bonds. So let's go through that. So the math of it all. And I'll set up my little table again, starting with our bonds broken. For CH bonds. And then we said 4 OH bonds. And let's look up bond strength. I want to say it's 431, but 414. I was off. Okay. Our carbon hydrogen is 414. But again, that's kilojoules per mole. So now I'm going to write that. So kilojoules per mole. But we have 4 of them. So maybe I'll write that out. So times 4, just so it's clear. Let me get out my calculator. So now that's 1656. And yell at me in the chat if I'm going too fast. Now let's look up our OH bond strength. So OH 464 kilojoules per mole. Now I'll write that. So 464 kilojoules per mole, and then times 4 once again. And let's see what that gives us. I get 1856. And 1,856 kilojoules. And might as well add this up to see how much total energy went into this process. So 1656 plus our answer. And I get 3,512 kilojoules. And I'll put a big plus sign so we can remember that's energy we had to put into the system. So let's switch over to our bonds formed. And I'm just kind of recapping mentally. Okay, 4HH. And we said 2 of these CO bonds. But I'm actually going to write CO2. And we'll see why in a second. Let me title my graph. The same process. Let's look up the values again. So HH. 436 kilojoules per mole. So I'll write that. So times 4. Let's punch that out. So 1,744 kilojoules. And then I want to point out this special thing. And we have two COs. Let's zoom in so we can see. So we have a CO bond, double bond, but then it has this asterisk next to it, and it says use a value of 799 for CO2. And so that's just telling us that this CO bond is for a different type. So when it's more like in an organic compound, something like that, like formate. But if we just have CO2, that's stronger. And so we should use this value instead. So that's the one special case. And then this is per CO bond. Now let's write that. Oh, there we go. 799 then kilojoules per mole times 2. And we should get a value of 1,598 kilojoules. So let's add that up to get our total energy out. So I'm going to put a negative sign in front of this. Now 1598 plus our 1744. So I get 3342. So 3,342 kilojoules. Exothermics, put a negative sign. Now we need to add these two together, get our overall energy, our overall change in enthalpy. And enthalpy, remember, is just the change in heat. We're just measuring our energy in heat right now. And so now we get a positive number, so positive 170 kilojoules. So energy had to go in, overall endothermic process, and would feel cold to us. Questions about that? Feeling okay? So let's look at our next section. And we've kind of gone through this. So this is just kind of summing it up. And so we saw that these energy diagrams were just a kind of graphical way of showing the energy flow. And we saw that we could have reactants where their energy is higher than the products. Their change in energy is negative. So this would be an exothermic process. And so we can also, and like we said, exothermic tends to feel hot. And so that's just saying that if we're studying our system, so this reaction would be our system, and then everything else is the surroundings. So whatever energy that was lost by the reaction has to go somewhere. Again, hence why you feel it. So the surroundings, aka, you. So you would feel that delta positive change in enthalpy. So feel that heat. We can also draw the diagram like this, and you might be asked to make a diagram like this on an exam, or draw one, or label one, or list the parts. So this is an important section since this is a pretty common reaction diagram. So we have on our x-axis time, and then our y-axis is potential energy here. So if our reactants are at a higher energy, And then so notice we have this transition state. So this is just this short-lived high energy state where the chemical is undergoing its transformation, and we have to, of course, also reach what's called this activation energy. I always like to compare that to, the activation energy it takes to get you out of bed. Probably have to entice yourself with some coffee maybe in the morning. And so then from there, from our transition state, we go to our products. And then this difference in energy, so the change in energy from your products and your reactants, so that's again your enthalpy, so your delta H again. And in this reaction diagram, note that your products are lower than your reactants. So this is showing us an exothermic process. Questions about that one? And so for comparison, let's look at the endothermic process. Again, we can look at this more simple graph where we have reactants lower than the products. And so that's showing us our positive change in enthalpy. So like we stated before, that energy has to come from somewhere, right? Conservation of energy. And so if our system is becoming positive in energy, that means the surrounding had to put in some energy. And so comparing the reaction diagram for our endothermic reaction, we see our products are now higher in energy than our reactants. So we can take this difference here. That's our delta H. And then notice we can still calculate our activation energy. So we still have that transition state. And so our activation energy is pretty large there. And so again, be prepared to kind of construct a diagram with all those relevant points labeled. So reactants, transition state, products, our activation energy that goes from reactants to transition state, and then our change in enthalpy, which is products and minus reactants difference. All right, let's keep looking at reactions and talking about reactions. And so we're just kind of taking a more cursory approach to this. And so now we're just kind of stating that we have what's called chemical kinetics. So this would be the study of how fast a reaction is converted to products or vice versa, how fast something is consumed. And it's important to be able to kind of control the speed of a chemical reaction, at least to some, abilities. So this is kind of a vague statement, but you could take it in a couple of different directions, right? You can think about industry where you'd really have to control that reaction. So you'd have a very controlled system, right? Because you have to know how much product am I making. You have to control that. You can't just, have all these wild unknown processes, especially from a chemical engineering perspective, right? Everything has to be optimized. So that's one way to think about it. But we also don't have to be so specific, but just maybe, either, at home or, in our lab, if we're trying to do something, how can we maybe try to influence the speed of something? How can we slow it down? How can we speed up a reaction? Maybe you're trying to even dissolve sugar. What are the basic principles that maybe allow that to happen a little faster? Or, if you go and continue in chemistry in the research lab, you might have a reaction that involves a lot of gas. And so you'd want to do that reaction really slowly so that gas can have a chance to bubble out and escape and not just explode your reaction flask or something or pop off your reaction. So there's lots of different ways to think about kinetics, right? So it doesn't always have to be so quantitative, clearly. And so, kind of looking at some things, and again, this is kind of where I wish we were in person in lab, but again, if you want to play around in lab with some of the chemicals that we talk about so you can get a sense of this, oh, I'm totally happy to facilitate that. And so we would expect a difference in reactions rates with our reactant concentration. And let's see. I was hoping to find a video now that I thought about it, but oh well, Google isn't pulling up what I'm looking for. Yes. Well, it might be in one of our lab videos, but there should be a lab where we compared 3 molar hydrochloric acid versus like a 1 molar hydrochloric acid. And so we see greater concentration that leads to a faster reaction. And so why that happens, you can imagine, right, them floating around in our beaker. But our 3 molar acid, right, is 3 times more concentrated. And so that's just a higher probability of them bumping into each other, colliding, and then having also more productive collisions. And so that's what it says here, right? Increases the frequency of our reactant molecule contact. And so that leads to, again, more reactions. And so I don't think we've quite gotten to the solution chapter yet. I think that's coming very soon, though, if I remember correctly. But we have what's called molarity, which I'll at least define what it is. So molarity is just a ratio of moles in liters. And so that's just telling us how concentrated. And again, all we need to appreciate is, more concentrated reactants equals faster reaction. And so changing the temperature can also increase your reaction rate. So they have this kind of in general statement, for every 10 degrees Celsius, the speed of the reaction doubles. But again, that's just a broad statement. But if you're trying to get something to dissolve, right, then you can heat it up or at least, warm it up gently. So it just depends on, again, what you're trying to do. And then the properties of the substance. So you always want to keep in mind like the boiling points and melting points of everything that you're working with. And so other things that we can use to influence reaction rates are called catalysts. And so catalysts are just defined as a substance that can affect the rate of the reaction without being consumed. And so we can see this mechanism here of ozone adding oxygen, an oxygen radical and then forming O2 is pretty slow. But then with a catalyst, so with a chlorine radical, a catalyzed reaction, that reaction occurs much faster. And so generally the catalysts are used and then they are reformed in a later step. So as shown here. And so let me kind of show some other. So there's also these other catalysts. So these Grubbs catalysts that are used for olefin metathesis. And again, catalysts work by providing a whole new pathway for these reactions. Let's see if we can actually find some of these reactions. And so it can do some of these ring reactions. And notice, right, it adds this bond across, and then you can eliminate this. Now you've made this new compound entirely. So this allows for ring opening metathesis. And again, all I'm trying to show is it's a completely new pathway, right? Because it's forming a new compound. I was hoping for kind of better schemes. This is decent, showing you kind of what's going on. So again, this like split across and then form new product that does not have the catalyst, reform your catalyst. Oh, what is this? Oh, there we go. And so your book also mentions the fact that most catalysts, at least when we say the word catalyst, this is generally considered a positive catalyst, meaning that it's speeding up the reaction. And it says that you can also use a catalyst to slow down a reaction. And this would be called an inhibitor. You might be more familiar with that term. So something that might block the active site and just prevent, the reactant from getting to where it needs to go in such a short amount of time. And again, appreciate this energy diagram. That's another way of showing what I was trying to show you with the Grubbs catalyst, was that here's our uncatalyzed transition state, right? High activation energy. But now that it goes through a different pathway, and this is just kind of an example that maybe it goes through two different energy states, but basically new pathway, maybe two different lower activation energy barriers, and then we get our product. Oh, and then other little bits of this. So if you have what's called a homogeneous or homogeneous catalyst, all species are in the same phase. And so this would be like, think of aqueous solution. Everything's again in the same phase. They're all aqueous ions, including your catalyst. And what you find is people tend to want heterogeneous catalysts. And so this would be species in different phases. And so a good example would be your catalytic converter. Catalytic on your car. So your catalytic converter is just a bunch of metal that reacts right with the gas coming across it. And so that would be an example of a heterogeneous catalyst. And often people prefer, at least again in industry, they would prefer heterogeneous catalyst since that allows for easier separation. Because part of the trick with the homogeneous catalyst, and that would be an issue, with like the Grubbs catalyst, is actually being able to separate and isolate out that catalyst. And so sometimes your catalyst is what I would say, right, just lost. And so this is still feasible since you usually only use like 1 to 10%. It's called loading of a catalyst. So whatever, right, your molar conversion, instead of using like a 1-to-1 ratio, you can use to a 1 to 100. So that would be like 1% catalyst to 100 moles of what you're interested in. All right. I'm just checking out what else we have. So our last bit is Le Chatelier's principle. And so this is kind of important for our lab. And so let's look at this process here. So now we're looking at hemoglobin. And so hemoglobin is our protein that's found in red blood cells. And so it reacts with O2 and kind of binds, right? So this hemoglobin is iron base. And so it binds to our oxygen and then transports it around. And so let's kind of talk about how this really works in a little bit more detail. So notice this equilibrium arrow. So what happens is, right, your hemoglobin starts off in your lungs. And so there's going to be a high concentration of oxygen in your lungs. So this high concentration of oxygen, and then probably also a high concentration of deoxygenized hemoglobin, right? Because it just came from your body. So the high concentration of both of these drives the formation of our complex hemoglobin oxide. And so then this compound, right, leaves your lungs and travels through your bloodstream, and then it goes down to your leg. And your leg has been exercising or running around, and so now it's oxygen deficient. So there's not a lot of oxygen. And so that lack of oxygen and now a high concentration of this complex hemoglobin oxide allows the release of that oxygen where it needs to go. And then, of course, this now deoxygenized hemoglobin travels back up to the lungs and starts the process again. And so this is just a quick recap on our arrows. Let's do another one. And I don't remember how much we've talked about this, but we also have what's called our resonance arrows. And so this is from moving electrons around. So this is a carboxylic acid group, but it's deprotonated, so it has a charge. So this kind of single double-headed arrow is for resonance, for electron movement. We just got done with a bunch of chapter 5 homework that had a bunch of single-headed arrows, right, showing us that our reactants are converted to all our products at the end. And so now this double-headed arrow, this double arrow with half arrows. So notice that, right? They're just little half arrows. This is our equilibrium. And so if something is in equilibrium, that means it can kind of go back and forth between the two from our reactants and products, depending on those conditions. And so that goes to the Chatelier's principle with what we were describing with the different conditions. So we saw how in our highly oxygenated environment that led to the formation of our product. But then in our muscle, we had a lot of product, no reactant, so it disassociated. All right, so hang with me for a little bit of math. And so we have what's called this equilibrium constant. And so roughly it's products over reactants. But let's follow along. And so notice this is a concentration of each one of these substances raised to the power of whatever it is in the balanced equation. So the lowercase letters represent the coefficients of the balanced equation. And this equilibrium constant does not have units, and it can tell us kind of which way the reaction favors, so products or reactants. And so let's look at this. So they've written out our equilibrium constant. We have 4NO to the fourth, since this is 4NO2, our balanced equation. One equivalent of oxygen, so times oxygen. Again, products on top. And then over our products, so over our reactant, dinitrogen pentoxide squared, since there's 2 in our balanced equation. And so kind of the quick and dirty of what we need to know is, well, what happens when our value is much greater than 1, this value of K? And we said roughly, well, it was products over reactants. So that's telling us in this reaction of H2 plus bromine to give us hydrobromic acid that it is favoring the products. So our K is 1.9 times 10 to the 19th. So that's a large number, again, favoring our products. If our value of K is small, so in this case, we're looking at this nitrogen plus oxygen gives us nitrogen oxide, so NO. And so we see that our K is really small, so 4.1 times 10 to the negative 31. Again, products over reactants. And so now we can say that our reactants are highly favored. And this makes sense because obviously if the products were favored of this reaction of nitrogen and oxygen, then there would not be a lot of air for us to breathe. Okay. So with Le Chatelier's principle, again, just like we were saying, we can disturb our equilibrium. So there's a lot of words here. Let's kind of look at this. Let's look at this graph here, because the graph is more telling. So we're saying we're looking at this reaction. So this is either the dimerization or the dissociation of dinitrogen tetraoxide here to nitrogen dioxide. And so we see the system was initially at equilibrium. And then if you disturb the equilibrium by adding, in this case, a bunch of products, so now that's going to cause a stress on the system. It wants to reestablish equilibrium. And so then it starts going and forming more of our reactants in that case. And then equilibrium is reestablished. And so again, same thing. We have our system at equilibrium. Now we've added more products, artificially spiked. And so now, again, this causes our reaction to disassociate more. And then we see more NO2 formed and our equilibrium reestablished. And so same thing, right? You can also drive the formation of reactions with Le Chatelier's principle. And so a lot of words here. Let's look at a type of example, another type of how to use this. So let's say you have a condensation reaction. And so all this means is that it's two things that form water. So you react two things together. Let's say AH plus BOH, and we get water plus AB. And so we're interested in AB. And so sometimes to get this reaction to go, we have this apparatus called a Dean-Stark apparatus. And so let me show you what this looks like. And so the Dean-Stark part is over here. And so you would have your reaction here. You'd be boiling it. So it'd be heating and refluxing. And so that would mean some vapors would travel this way. And then you have your water here to condense those vapors back down. And so then your reaction starts collecting liquid over here. And so usually you're doing this reaction in some sort of organic medium. So then what's going to happen in that little tube is that you'll collect, let's just say like your ether on top, and then your water will be at the bottom. So you wouldn't want to use an organic solvent that's denser than water, which there aren't that many, but there's like dichloromethane or DCM is one of them. Oh, now I lost my Dean-Stark picture. There it goes. And so your water starts collecting here at the bottom. And if it gets full, this is a little stopcock, so you can open it up and drain off your water. And so it kind of breaks that all down there in schematic. But the point is, so why are you trying to collect off the water? Well, you're trying to remove the water from your reaction such that if you remove the water by Le Chatelier's principle, it wants to form more product. So then you're going to keep driving the formation of AB because you're removing one of the products, water. Is that clear? All right, let's kind of look at the text. But basically, we're saying, okay, we add a reactant, and then it has to be something that affects the concentration. And so, right, not just like a liquid reaction. And so this would be like a solution would be okay. That's fine. But, right, it can't just be a solid or a straight liquid reaction because then that's implying like neat is what this is saying, or you have like two liquid reagents or one liquid reagent and one solid one that can kind of act as a solvent. And so now it says again, if you add reactants, we would initially increase our rate of our forward reaction, and then there would be no effect on our reverse reaction, and then we restore our equilibrium. And then again, right, equilibrium is restored, but now you have kind of, this is all a convoluted way of showing what was going on here, right? That we have more of our added reactions, reactants, but not as much as we had added. And then we have more of our products. It's kind of convoluted. And K is never changed. Your K is a constant. And so again, you remove a reactant. And so if you remove a reactant, this would decrease your rate of the forward reaction, no effect on the initial, but then overall it's going faster in reverse until, again, our equilibrium is established. And K is unchanged. So that's the only key, or the other key is that your equilibrium constant is always the same at that temperature. So change the temperature, you change the constant, but we won't be doing that in this class. All right. I think that's a good place to end. So we've covered all of our chapter 6, it looks like. Definitely email me if you have questions. We can always set up meetings. This afternoon, there still could be time if you email me. Fridays are always a good day. I can meet Thursdays. Just email me, let me know. And otherwise, keep up the good work. And I will continue to catch up on grading. All right, I'll hang around again on stream in case there are questions. Otherwise, have a great day.